In this video, we will be delving into the theory and art of titrations. A titration is defined as the process by which the concentration of an unknown solution is determined through the controlled addition of another solution until everything is completely used up. It is important to take a moment to note another concept we've seen before, limiting reagents. In limiting reagent problems, something is always left over. Say, for example, if we started with 5 moles of some substance A and we added 3 moles of B. If A and B react with a 1-to-1 molar ratio, what will be true at the end of the reaction? Since B is the limiting reagent, there will be 2 moles of A left over at the end of the reaction. But when it comes to titrations, there is no limiting reagent. We are titrating until all of the moles of our unknown solution are used up, and this will be equal to the mole of the amount of titrant that we added. We won't be having any excess of the solution we are titrating. So, in our example, we would have to have 5 moles of B to completely titrate all of A that we started out with. Let's explore in greater depth. Titrations use this apparatus here. Titration calculations can get quite complicated at first, but if we work through the problem systematically, we can use knowledge that we already know to help us solve the problem. Let's brush up on some basics really quick. You are a baker, and today you have your routine amount of cookies to make for the day. You have 13 cups of flour, 10 teaspoons of vanilla extract, 12 eggs, and 7 cups of brown sugar. Per batch of cookies, you only need 3.5 cups of flour, 3 teaspoons of vanilla extract, 1.5 cups of brown sugar, and 3 eggs. You are making multiple batches of cookies at a time using the ingredients you have, and your employee is only making 1 batch of cookies to try out a new recipe. Which of these examples is like a chemical reaction with a limiting reagent? That's right. How many batches we make depends on which of our ingredients runs out first. This illustrates the concept of limiting reagents. Now, which scenario would be like doing a titration in regards to using up our reagents? That's right. When we use up all of the ingredients or reactants exactly with nothing left over, then that is a titration. Let's get back to some chemistry. Understanding stoichiometry is a very important necessity in solving titration problems. Let's look at an acid-base reaction between hydrochloric acid and potassium hydroxide. What is true about the stoichiometric ratio between HCl and KOH? That's right. Here we can see that we have a 1-to-1 ratio of our HCl to our KOH. This means that for every 1 mole of HCl in the reaction, we would need exactly 1 mole of KOH for both to be completely consumed. In titrations, we call that point, where we've added exactly enough of one reactant to completely consume the other reactant, the equivalence point. The point in the titration where all of the moles of the solution we are titrating has been used up by the titrant. Let's try a titration problem together. Still discussing our reaction of hydrochloric acid and solid potassium hydroxide. We have a solid sample that contains 0.0025 moles of KOH, and we are going to titrate this sample with a solution of HCl, whose concentration is unknown. A total of 15 milliliters of HCl is added until we reach the equivalence point of the titration. How many moles of HCl were present in the 15 milliliters that we added? That's right. We know that the sample contains 0.0025 moles of KOH, but how can we now relate this to how many moles of HCl was added? The stoichiometric ratio. We have a 1-to-1 ratio of HCl to KOH. So, doing dimensional analysis again, crossing out our similar units, we get 0.0025 moles of HCl. What is the concentration of the unknown sample of HCl? That's right. The 15 milliliters of HCl solution contains 0.0025 moles of HCl. Dividing the number of moles by the volume, we get 0.17 molar. Now that we've solved a nice simple problem, let's move on to a more complicated one. As the town detective, you've been tasked to figure out why so many fish and frogs are dying in a nearby river. You've come to figure that there is a substantial amount of phosphate ions in the river. You need to determine the phosphate concentration to report back to your boss so that it can be properly handled. Your partner pulls out his burette stand and performs a titration, stating that 35 milliliters of 0.42 molar solution of calcium hydroxide is needed to reach the equivalence point with 20 milliliters. Partner thinks that it must be a 1-to-1 ratio just like the previous problem, but you know better. The unbalanced reaction is as follows. What is the stoichiometric ratio between calcium ions and phosphate ions? Well done. You figured out that the stoichiometric ratio between calcium ions and phosphate ions is 3 to 2. That makes the balanced reaction as follows, and the conversion factor for stoichiometry is 3 moles of calcium ions to 2 moles of phosphate. The magic word in the problem is titration. That tells us we know that all of the reactants will be exactly consumed during the reaction. So let's draw a beaker that reflects this scenario. We have river water with an unknown number of moles of phosphate ion. Let's use X for the moles of phosphate. And we know that the volume of the sample is 20 milliliters. Let's write that under our beaker. Next, we titrated with 35 milliliters of 0.42 molar solution of calcium hydroxide. Let's update our beaker. What should we add into our beaker? Dimensional analysis shows us that 0.035 liters times 0.42 moles of calcium hydroxide per liter gives us 0.0147 moles of calcium. Of course, we know that this is an ionic compound, so that is 0.0147 moles of calcium ions in our beaker and 0.0294 moles of hydroxide ions in our beaker. Let's add the volumes to the bottom of our beaker, but don't combine them just yet. Based on our beaker, what was the concentration of phosphate ion in the river sample? First, we need to determine the number of moles of phosphate ion that was in our beaker. We know that the moles of calcium ion are completely used up since this is a titration. So this gives us 0.0147 moles of calcium times 2 moles of phosphate per 3 moles of calcium ion, which is 0.0098 moles of phosphate ion. The final question is, what volume do we use? 55 milliliters, 35 milliliters, 20 milliliters. Remember, all of the phosphate ions came from the 20 milliliter river water sample, so that the river water's phosphate ion concentration is 0.0098 moles divided by 0.02 liters, which is 0.49 molar. That's really high. We better report this to an environmental regulatory agency right away.